Hello, calculus students. I hope everything is going well with you. This is the video for section 5.2. So in the previous section, you learned how to take a double integral over a region that is rectangular. So the natural question is, next is, what if the region is not rectangular? So that's the topic for today, all right? So let's get started on section 5.2. All right, so before we go into the non-rectangular regions, I wanted to point out a couple of things about the nature of double integrals. Okay, so I mentioned that sometimes you can't do or you can't evaluate double integrals with a given order. And in that case, you may have to do something else, right? So let me explain what I mean by this. We want to find this integral, let's call this capital I, which is a double integral of xy times e to the xy squared dA, where r is defined as, and I'm going to define this as a 2x1 rectangle. All right, I know that eventually we'll be talking about non-rectangular regions, but here r can be defined as the Cartesian product of 0, 2, times 0, 1. Okay, so I mentioned what this means, right? This is a set of all xy such that x is between 0 and 2 and y is between 0 and 1. All right, so how do you do this? All right, so one way to try to do this is maybe try to write this as yx times e to the, remember here, I am going to write this, because 0, 1 is the bounds for y, we are thinking of this as dy dx, sorry, dx dy, right? dx dy, because the x has the bounds of 0 and 2, and y has the bounds of 0 and 1. All right, so I am going to write this as e to the y squared times x, okay, because that's what this is, right? And I have to integrate this with respect to x first. So then you start to go like this, and what is the antiderivative of this big ugly thing here? Okay, let's use another thing here to write what this is. Y times x times e to the y square. Now remember, this is what we're trying to find out. Okay, and so I need a function so that its derivative with respect to x is this, all right? And so what is that? Can you think of a function? Maybe y is a constant here, but I need to have I have to have x here, and I have to have e to the y squared x, and I need to find a function whose integral whose derivative with respect to x is this, right? And you find out it's really hard. And in fact, it's impossible to do, okay? So after you scream and you say, ah, okay, then you say, all right, so I can't do it this way. So there are oftentimes, okay, there are many situations where you set up an integral in a certain order and you find out you cannot do it in this way. And that is why we have to study this thing, non-rectangular regions. And more importantly, we should be able to figure out how to switch the order, okay? And sometimes it works. There's no guarantee it's going to work, but sometimes it does work. And so I will be showing you how that would work in this situation. All right, so I just switched the order, all right? So now the x numbers are here outside from 0 to 2, and y goes from 0 to 1. All right, and let's see if this will make any difference in this situation. Now I have to find a function whose derivative, did I write this correctly? I don't think I wrote this correctly. This is supposed to be x, right? Okay, so now what I will be looking for is a function so that yx times e to the x y square dy. All right, so with respect to y, can I find something like this? And so natural thing here, a natural thing to do is, because I have this compound or composite function e to the x raised to the y squared, u, let u be e to the x. Okay, so then du is, no, I guess I should not do that. All right, let's do, because I have y squared here. You know, e to the x is like a constant here, right? Y squared, all right? And then you have t, 2y dy. Now, this is not exactly that, but I can cut this in half, right? And then I have x e to the x, y squared. And remember, you have y dy here. So this will be 2y dy. See, I have, yeah, let me just go ahead and write it this way, 2y dy, right? And you know how the u substitution works, right? That's, by the way, one of the best things that you have learned in integration. That's the u substitution. All right, so far, all I did was to divide the outside by 2 and multiply the inside by 2 so that you get to see this. Right now, does this actually help? All right, so inside is x e to the xu, looks like, right? And then you have du, okay? And so then we take a look at what I can do next. Okay, and so I think you can see that this will just be 1/2 times e to the xu plus c. Now, do you see this? Because as far as u is concerned, x is just a constant, right? So in other words, if you have e to the 5 u, if you differentiate this, you get, let's put diff, differentiate this, you get 5 times e to the 5u, right? Okay, as far as y or u is concerned, if you have e to the xu, if you differentiate it with respect to u, you get e to the xu times x, because x just is like a constant, right? So that's why you can go from this line to this line, all right? So over here, I can rewrite this. Let me just go ahead and rewrite this way. It's 1/2 and I'll go back to, let's go ahead and go to a red line here, red ink. So, so far, oh, by the way, when I do this, so you see, remember y goes from 0 to 1, right? And so when you do the u substitution, then u is going to go from 0 squared to 1 squared. Well, 0 squared to 1 squared is still from 0 to 1. So the new bounds are still going to be 0 to 1, all right? And this y dy has kind of gone away. Maybe I should rewrite this way here, x e to the xu du dx, all right? So this is the part I am working on here. And so now this is 1/2. And remember this part here is going to be, and maybe I should use a different color here too, right? Let's go ahead and write this part as a purple box here, right? That part, okay, becomes e to the xu, right? That's what I was trying to say here. 1/2 is already being taken outside, so that's okay. E to the xu, if you differentiate this with respect to u, you get x times e to the xu, right? So this is the correct antiderivative for x times e to the xu, right? So then this becomes a simple integral now. It is, remember, you are plugging in 1 and 0 for u, so it's e to the x, 1, minus e to the 0, which is 1, all right? And so now this is a calculus 1 problem. It's e to the x minus 1 dx, and so that's 1/2, and then you have e to the x minus x. I'm plugging in 0 and 2. Now remember, e to the 0 is not 0, so you don't automatically lose a term here. This is e to the 2 minus 2, minus, and then if you plug in 0, you get e to the 0 minus 0. Yeah, right. And so this is 1/2 e to the 2 minus 1, and so that's minus 3. And so that's your answer, right? So it actually paid to switch. So sometimes, let me just go ahead and write down the takeaway from this, or the moral of the story is sometimes you have to change the order. Right, and so in this case, the switching, the changing the order of integration was easy because it was a rectangular region. 0, 2, 0, 1 became 0, 1, 0, 2, right? And so it becomes a lot more complicated issue when you have a non-rectangular region. And that really is what makes it important for you to learn this section, all right? Now, let me just give you a little hints. And this is not the hints about switching the order, okay? But one thing is you should use symmetry whenever possible. All right, maybe I'll just say it's a hint because, yeah, that's okay. Okay. Use symmetry whenever possible. What do I mean by this? All right, so do you know what the integral of negative 10 to 10 x cubed dx is? Right? You should know what the answer is. Maybe I should say 100. Okay. You know what that is? Okay. If you said 0, you are exactly on up to what I'm trying to teach you, right? Because x cubed have this symmetry, which is called the odd function. It is symmetric with respect to the origin, right? So as long as this number and this number are the opposite numbers, these areas cancel each other. So the answer is 0. Okay, and the reason it's 0 is because both sides canceled each other. All right, now let me ask you this. If you have a double integral over the region R of y sine x dA, where R, let's say R goes from, well, let's see, like this is 2, from negative pi to pi. This is your region R, okay? Your region R is this big rectangle. This is a 2 pi times 2. Okay, that's a big rectangle, right? So what is this answer here? Well, you know the y is going to be positive, all right? And it's going to range from 0 to 2. But for each y, okay, set each y a constant. As x goes from negative pi to pi, so what does that function look like from negative pi to pi? The sign of x will be going like this, right? Okay, so for each thing, each y fixed, whatever that y is, maybe 1 or 0.3, you know, any number, y can be any number between 0 and 2. For this, sign of x will go like this, and then like that, right? So they cancel each other, right? So the answer has to be equal to 0 because for each slice at each y slice, the graph is going to look like this. Now, as y gets bigger, you know, of course, this gets more like this and twice as big as that, okay? But the areas will always cancel. The left-hand side will cancel with the right-hand side, so it's going to be 0. All right, so that's one thing that you should know. Number 2, do you remember the average area or average value? Okay, what is the average value of a function? So the idea was this: if you have a function like this, you know, the average value is sort of like, you know, where you can cancel the top part here, will cancel with the bottom part, you know, and so this thing is called the average value. Let's call it f of AVE. So the average value f, which is called f sub average. All right. What is this average? Okay. Well, the average is so that average times a, you know, the length b minus a. See, you want the f of the average value to be this height, okay, the y value, so that this times the length of the interval b minus I is equal to this integral, right? See, that's what I mean. In other words, if you think of this as a sand dune, you know, say this is a sand dune, or like a pile of sand, okay? You want to shake this around, you just shake, 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 and you want this to be flattened so that this top part will just go and fall into the bottom part. This is your average, right? And so to say this times this is equal to that, so you can tell what the average value is. The average value is the integral from A to B of fx dx, that's the entire amount of sand, and you divide it by the length of the interval, right? And that is your average. You remember that, right? So now, if you have a some region R here, okay, and over on the top of the region is your function, okay, which depends, of course, on x, y, right? What is the average value of this function f over the region? Right? It's going to be the same as this. It's AB, it's, well, sorry, it's not the same. It's double integral over the R, region R, of f of x, y, dA. So that would be the volume of the solid under the surface of F, right? And you divide it by the area of R. Okay, so again, you are flattening this. If this is a sand pile, you're just shaking this, just go shake all over here until the top becomes flat. And then, you know, that would be your, this will be your average value of F over the region R. So you can also write this as the double integral of R of F dA divided by, remember what the area is? That's just the double integral of, okay? Just like over here, we could have written this. Normally we don't do this, but we could have written this with the denominator, the integral from A to B of dx, which is exactly this. All right, so keep this in mind because we'll have questions about average values, okay? And remember, symmetry is your friend, okay? Use symmetry as much as possible and as often as possible. Okay, so now let's go to the question we started this lesson with. What if R is non-rectangular? Then what do we do with this? Okay, so let me explain how to set this up here. And I'm going to be giving you examples as opposed to giving you a simple way of doing this or a general rule, because the general rule is kind of hard to explain. Right? Even if I could say that, it'll be kind of difficult to actually implement it. All right, so here, let's talk about this line here. Okay, now this line, and we have a horizontal line. All right, so what do we have? This is the origin. This line is y is equal to 2x. This is 2 here, and 4 is y. All right, and this is my region R, okay, of integration. See that? Okay, I am going to integrate f, and let's say f is x squared y, and integrate, find the double integral of fxy over the region R. All right, so what do I do? This is clearly not rectangular, right? So this is what we will do. And I will show you how to do this in 2 different ways, okay? So first, number 1, let's use the order dy dx. All right, now follow along, follow this very carefully because this will lead us to the discussion in the second part of this section called type 1 and type 1 region, okay? It turns out this particular R can be thought of as both type 1 and type 2 regions, and I will explain that later. But R in the order dy dx, that means I will do the integration of y first and then x later, right? And here's what I would suggest, and it may be different in different books you read, but I find that I think it's the most helpful. See, the idea is you're going to come up with this. This is the final result, okay? You're going to come up with a double integral with 4 bounds, you know, 1 for x and 1 for y. And so you're going to have this, and then I want eventually to write dy dx in this order. That's the first order that I'm asking you to do, or I'm showing you how to do. All right, so what do I have? I need the bounds for x here, and the y is in here. Right, now notice here, this is the first part I do. So once I'm finished with this part, okay, once I'm finished with this part, I can still have x in it. But once I'm done with this, I can't have any y values left over once I'm done with this. Okay, so that means these values could have x in it, and of course these have to be constants. Okay, let me show you what I mean by that. So I need to have the bounds for y at x first. And so you pick the biggest x range you see here. So x ranges from what to what? Okay, so let me go ahead and write this down. What's the range of x? Okay, what's the range of x? So x goes from, x ranges from what to what, all right? And you can see that there are regions of R where x actually goes from 0 to 2. Right? Now over here, around here, x doesn't go from 0 to 2. Okay, but there is a part where x goes from 0 to 2, right? In fact, the entire R can be fit into this range when x goes from 0 to 2. All right, so then that would be the first thing you do. Okay, and then the next thing we do is this: what are these? Right? So here's the question you want to ask. Listen carefully. This is very important. Once you decide x ranges from 0 to 2, okay, these are set. And then the question is, here's a question for each x, okay, between 0 and 2. Okay, for each x, let's say pick an x here. Then the question you ask is this: y goes from what to what? Okay, so if I pick the x, watch carefully, watch really carefully. All right, if I pick x here, y goes from this point to this point, right? Now the top bound is easy because it's always 4. Okay, if x is picked over here, x goes from here all the way to here, right? So y, the answer is this: y goes from wherever this point is for this x, and that will be determined by the value of x, right? If x is up here, x looks like 1.5 here, then this is like 3. And if x is near 0, let's say 0.5, this is 1. How do I know? Because on this line, y is always 2x. Right? So y goes from 2x, whatever that x is, to 4, regardless of what the x value is, because y always ends at 4. Okay, so here, if x is, let's say, 1.8, then y at that point is 3.6 all the way to 4. Okay, if x is 0, y goes from all the way from 0 times to 0 all the way to 4. Okay, so whatever the x values for each x, y goes from 2x to 4. And so therefore, this is the way we set up the integrals. 0 to 2, x goes from 0 to 2. And for each x between 0 and 2, y goes from 2x to 4. Okay, these tiny numbers, we just found these two tiny numbers, 0, 2, and 2x and 4. You would be spending a lot of time trying to figure out exactly what these upper and lower bounds are. All right. And then, of course, the integrand is x squared y, that's a given. And then you write dy dx in that order, right? Okay. After this, it becomes pretty simple. I don't think you'll have any problem evaluating the integrals after you set this up correctly, right? The hardest part is to find these 4 little bitty numbers, okay? You will spend a lot of time trying to figure this out, but once it's done, it's not too bad. All right, so let's try to integrate this with respect to y. You get 1/2 x squared y squared. We're okay with this? X squared is considered constant at this point, right? And so this is what happens here. Now the rest is, it could be tedious, but it's not terrible, right? So this will be 1/2 x squared. And remember, these are the y values. So you put 4 square minus 2x quantity square. That's what goes into y square. All right, so I'm still working on the inside. Actually, let's take this 1/2 outside. You don't have to do it, but I always try to take constants outside anytime I can. All right, the inside of the parentheses is 16 minus 4x squared dx, all right? And then we can simplify the inside. That's 16x squared minus 4x cubed, sorry, x to the fourth. And then you do dx, x goes from 0 to 2. All right, not hard, okay? This will be 16 over 3, x cubed minus 4 over 5, x to the fifth, going from 0 to 2. It's not a very nice number, but that's going to be 16 over 3 times 8, right? Minus 4 over 5, and 2 to the fifth is 32. Okay, so then this is how you get your answer. Now, it's still not a very pretty number, but you have 1/2 over, the denominator is 3. The numerator will be 128, okay? And then here you have 5, and then 4 times 32 is 128, all right? And then, of course, you can simplify here. You can get rid of that. That's 64, and that's 64. So the answer will be 64 over 3 minus 64 over 5. Okay, so that's what you can get. And by the way, this, if you calculate this, it becomes 128 over 15, right? Because you can find the common denominator and so on. You don't really have to do it this much. This part will be perfectly acceptable. All right, so that's if you decide to do it in the order dy dx. All right, now before I pause this, I want to show you the other way. All right, how can you write this as dx dy in that order? All right, so I am going to draw the picture again to show you exactly what's happening. All right, so pay close attention again. All right, so this time I need to write this in this order, right? Dx dy. So the first thing I ask, I'll go from outside to the inside. Y goes from what to what? Okay, and the answer is y goes from 0 to 4. Again, find the biggest area covered by y. You know, y ranges from what to what in order to cover this entire region R. Well, the answer is y goes from the lowest part of 0 to the highest part 4, right? And then, again, then for each y I pick, you know, I'm going to now wonder about the slices. If I stop this y at some, if I pick a particular y, remember, because this part y is held constant, pick a particular y, and you ask the question, then for that y, x goes from, remember, x goes from left to right, you know, smaller to large, x goes from this point to this point. How do I describe that? Okay, if I pick y here, y goes from this point to this point. Now, the lowest number is always 0, right? So that part is easy. Then for each y, x ranges from the lowest number 0, it's always 0 here on the left-hand side, to whenever it hits this point, okay? Well, this point is always on this line, y is equal to 2x. But I need to know what x is based on this y I chose, right? So in other words, I need to rewrite this. Some of you may hate this. I need to rewrite this in terms of x. Solve this for x. Yeah, I don't like that. Well, yeah, I never liked it either. But so it's not too bad, right? In this case, y is just 1/2 y. Sorry, x is 1/2 y, or y over 2. Okay, so, and it makes sense when, let's say when, and I mentally try to do this, if y is halfway here, 2, okay? If y is 2, then according to this, the x goes from 0 to 2 over 2, 1, and that's exactly this. So that's good. At the upper bound, when y is equal to 4, this means x goes from 0 to 4 divided by 2, 0 to 2. There you go. Okay, so this is the correct, these are the correct bounds for this. All right, so that means my integral is y going from 0 to 4, x goes from 0 to y over 2. All right, now let me again highlight this fact. This part has no variables. You cannot have any variables at this point. But for these, you can have not y, because y is okay, but not x. because once you're finished with this, you shouldn't have any x in here, right? After all, you are integrating with respect to x. So these numbers should not have x in it, right? So let me go ahead and write this down again. 0 to 4, and then x goes from 0 to y over 2, and then the integrand was x squared y, and then this time you do dy dx in that order. All right, the rest, as I said, is not bad. All right, so what do I get here? Y is a constant with respect to x, and you have 1/3 x cubed, and you plug in y over 2 and 0 and perform that subtraction. Okay, so then this becomes from 0 to 4, and you have y and 1/3, and then you have y over 2 to the third power minus 0 to the third power. Okay, lots of things happening here, but let's simplify this. You have y over 3, and then you have y cubed over 8 dy, right? So let's move the constants. 1 over 24 is out there. This becomes the integral from 0 to 4 of y cubed dy. All right, that is equal to 1 over 24 of 1 over 4 y to the fourth. Remember, this y cubed becomes y to the fourth over 4, and then from 0 to 4. All right, so this may look ugly, but that's not too bad. On the top, you just have 4 to the fourth power, okay? In fact, let's go ahead and write 4, 4, 4, 4, because it's 4 to the fourth. So you don't need a calculator necessarily, because you know that lots of 4s will cancel here, right? You can factor out a 4 here. This becomes 6. This, another one is canceled. And so the answer is, well, let's get rid of this and make it a 2, and then make it into 3. So this is 3 over, I think there's something wrong with this. I'll fix this in just a minute. 8 over 3, and something's wrong. Let me fix this. Okay, I hate it when nobody is here to correct me. You should have shouted out and say, hey, something's wrong here, right? Because you have y here and y cubed here, so that's y to the fourth. Right? I'm going to make all the changes with the purple so you know what I did wrong the first time. Okay, so this is y to the fourth, right? And so this is 24, 1 over 24. And here I will get 1 over 5 x to the fifth. Okay, so then let's cross out all of these, and I will fix that. Okay, so this is 1 over 24, and then you have 1 to the fifth, and then you have 4, 4, 4, 4, 4. It's 4 to the fifth, okay? And of course, now I can get rid of, this becomes 6, and this is 1 canceled out, and then this will become 2, and then this will become 3. And so the answer, the denominator is 15, and on the top you have 4, 4, 4 times 2. That's 64 times 2, and that's 128. And so the answer is 128 over 15, which is what we got in the first time. All right, so this is a great example, all right? And you know that one time, I mean, you have to write the same equation, y is equal to 2x as y is equal to 2x. And on the other hand, you have to write this as x is equal to y over 2. So that happens, and this explains, or this gives rise to these two terms called type 1 and type 2 regions, with which we will start the second part of this recording.